Okay. So while people are playing with the light, let me introduce. Oh, or do you want to?
I mean, I would introduce you, but you introduce yourself.
No. You're welcome to that.
So yeah, Timo wanted to introduce himself, but very briefly. So he's a doctoral student here at ETH in the systems group, and he's been working with us since, like, I would say 4 years, almost 5. And yeah, he's been working with NPI. He's doing a lot of networking stuff, some compiler stuff, and what he never did as a researcher is security stuff. But a lot of his spare time he spends in like reading security papers, and so he decided to give one presentation about a topic that's very hot at the moment. And yeah, so let's listen to the presentation and see if there's some more introduction Timo can do.
Okay. Welcome to this talk. I'm really sure all of you have heard about the Meltdown and Spectre vulnerabilities that has been all over the news. What I want to do in this talk is actually give you some more detail. So what we will not do is we will not go into kind of new research. So as a disclaimer, I am not involved in either the discovery or the mitigation of Spectre and Meltdown. I'm just a researcher in the SPCL lab. My background, as Tobias said, is HPC and a bit programming models, and security is a hobby, but even there I'm mainly focusing on RF stuff. However, I still think I'm a good person to give this talk because I have a strong background in computer architecture, and Spectre and Meltdown are not like many other vulnerabilities that have been detected, kind of bugs introduced by a programmer that wasn't careful, or mistakes that somebody made when implementing a protocol, but rather they are a consequence of years of computer architecture innovation. So a lot of the things that we will see today, when they were introduced, people were very proud of them, and there was a lot of research papers that were like, yeah, this improves performance by so many %, we need this, and everybody agreed. And that is why this topic is very interesting for us as a group, because we mainly do, or most of our members come from a computer architecture background. If you are interested in the computer architecture part of this talk, and you're a student at ETH, then it might be worth taking a look at our page where we list open thesis topics. So what is computer architecture anyway? So computer architecture is all about one sentence: computation is fast, storage is slow. And most of the stuff in computer architecture deals with how do we address this problem. We cannot solve it, right? So we can't make storage fast magically. We could make compute slower, but that would be kind of cheating and useless. So basically, we are trying to come up with tricks to solve this problem. And one of the earliest tricks and one of the most well-known is caching. So we have our compute core. Our compute core is connected to L1 cache, which is connected to more levels of caches. The problem with these caches is they are, okay, the good thing is they are very fast. The bad thing is they are very expensive, either in the amount of power they use per bit flip, or just having them on the processor die is expensive because it takes a lot of space, or in other ways expensive. So basically we can only make them small. So we can basically have a trade-off between fast memory and big memory. So a disk is really slow, but it's really cheap per byte. And the L1 cache is really expensive per byte, but it's really fast. So what we do is we mix both to make the latency of accesses smaller if we, for example, repeatedly access the same data. Another computer architecture innovation was out-of-order execution. So this is the famous Tomasulo scheme. If you are interested in the details how this works, the idea is basically we can not only take the next instruction. So as a programmer, of course, we expect that if we write a program, it's executed top down or however the control flow of the program dictates. What a CPU can do is actually take an instruction that is close to the next instruction, but it's not really the next instruction, but maybe an instruction that might be the next instruction, use, for example, the floating point unit to execute this instruction, but store the result not in the real register where it will be stored, but in some kind of reservation station, and then even use this further. So this kind of reservation stations serve like temporary registers, and the CPU is able to execute things out of order and just make sure that things are committed in order. So this was a really cool idea. The guy that came up with this is very famous. So this Tomasulo scheme, every computer science student knows about it at some point. I hope, at least. But both of these things combined will actually lead to the Spectre and Meltdown disaster, as we will see in this talk. So I think I talked enough about caches. So basically the idea is trading off speed and costs. And once data is in the cache, we can execute it the second time much faster. And that is the whole idea. And also a cache is typically, at least on x86, it's not on no other architecture that is popular. A cache is not flushed on a context switch. So if we switch from one process to the next, basically we can get some information even passed between processes, right? And this has never been regarded as a real problem. There have been papers about, whoa, but this leaks some information about the access pattern of the other process, if we know how addresses are mapped in the cache, but was never really a big problem. So this is a typical picture that you get from a program, I think it's called HWlog, that shows you how your cache in your machine is organized. So you have these 4 CPU cores that have hyperthreading, I suppose. That's why we have these 2 units in each core. And then we have a L1 instruction cache, a L1 data cache that are separate. We have a L2 cache that is for both. And then we have a shared L3 cache across the cores. This is a very typical modern CPU nowadays. The interesting thing is we can use this to communicate information using the latency of a memory access. So imagine we have one part of a code that loads something into the cache or not, and another part of the code that just accesses the same data and measures how long did it take to read that data. If that data was not accessed before, this should be slow because the data is not in the cache. And if the data was accessed before, this should be really fast. And in this way, we have created a so-called side channel. So we have no explicit communication between the 2 parts of the code. If you look at the code, there is no send or receive or write to a file or something, but still we can transmit information. So we can use that. And the next cool innovative computer architecture feature we talked about briefly was out-of-order execution and speculative execution. So what is the idea here? So even with caches, the CPU is often just waiting for data because the data is not in the cache, and even the latency for the L2 cache is already quite high, right? So the idea is do something useful while you are waiting. And in this code, we can see we have an if here, and we are comparing, well, if x is smaller than array1 size. I think this is very common. Every one of us has written this many times. It's just a kind of bounce check on an array. This x is supplied from the outside. Let's say it's user input, so we can't just blindly use it to index this array. And the problem is if we encounter this comparison and array1 size is not in the cache, then we have to wait a long time for this value to arrive. And what the CPU does in the meantime is it says, well, let me take an educated guess what will be the next instruction. So Why is this gas an educated gas and not a random gas? Because we have some hardware or some mechanism in the CPU that is called a branch predictor that says, well, I ran this code before, and basically the last 50 times I saw this branch, this comparison yielded true. So probably it will also yield true now. So let's assume that this branch is true, and let's use these cool reservation stations for all the following computation that we do based on this educated guess. If it's wrong, we can just roll back. We can just say, okay, we know at this time we took this guess, and if the guess is wrong, we roll everything back. We act like nothing happened. And if the guess was right, then we are happy. Then we did something useful in the meantime while we were waiting for this data, and we commit everything to memory in the right order, and it will look to the programmer that, yeah, my CPU is really fast and it's executing everything in order. This is what we want, and what has worked for many years. So yeah, what the CPU does, it already starts executing this line that accesses first array 1 and then array 2 based on the result, and stores the result in Y. And if the guess was wrong, we can just undo any changes we did while we were doing this. So this is the cool idea about out-of-order execution or speculative execution. And to understand Meltdown fully, we need some other cool OS or computer architecture feature, virtual memory. So in any modern OS, memory is virtualized. That means we have a pointer. Nowadays, pointers are 64 bits in size, and physical memory is not always the same size, right? We can buy more RAM or remove RAM. So that is really cool for us as programmers. We don't need to ask like how much memory do you have? If you only have 4 megabytes, then you can't run this DOS program. I remember those days. So basically, now we have this virtualized memory. As in a program, we always assume we have 64-bit pointers and we can use them. And the operating system somehow takes care that it looks like as if we had a 64-bit address space. To do this, memory is split into blocks. Usually these blocks are 4 kilobytes in size. They are called pages. And for each page, the operating system, together with some hardware, this hardware is called a memory management unit or MMU, needs to check where it actually resides in memory, and also if we are allowed to access this page. So if a process tries to access an address, we have some mechanism in the OS and in hardware that checks where in the physical memory this address actually resides. If it does, maybe it's swapped out. And if we can access this. If we can't access this, then what happens is the famous segmentation violation or seg fault in Linux. And I think in Windows it's just a blue screen. I don't know what the new Windows do when something like this happens. Maybe the screen is still blue. I don't know. And you can see here in this picture, right, we have this nice yellow virtual memory that is per process, and each process can decide what it does with this virtual memory. And then we have a mapping to physical memory, and this mapping doesn't need to be direct, so this can look very disorganized, and there can also be some other process residing in the physical memory, and the two processes don't know about each other. And the operating system to save physical memory, can put some of the pages on the disk. That is called swapping. Everything is amazing. How this is implemented is that each process has a page table. Usually the page tables have multiple levels, because if we would have just one big table and we would have 64-bit address space and 4 kilobyte pages, then you can calculate how long your table would be. It would be very, very long. And so we don't want that. We make this kind of multi-level table. We have this page table base register that points to the first entry in the first table. And we take some bits to address which entry we want to use for this address. And then we go to the next level and we take another set of bits to choose which of the second table. And of course there are many second level tables, right? I draw here just one, but each of these entries points to one table here. So this entry points to a table here, this entry points to this table, this would point to the next. This is how these multi-level page tables would work. And then only the last few bits are actually used to add this to what we get here to address data within the page. So that is paging, and it's amazing because what we basically get in the second level page table, we have some bits per page that are permission bits or flags, and in these permission bits we can say, well, this page exists, but this process cannot access it. That is great. We will see later what we do with that. We will see that now. So each user process has its own address space, right? We heard that before. And the kernel could be treated like any other process and have its own address space. And when we switch to the kernel, we just switch the value of this page table base register, and then the translation works as normal. But the problem is that we switch from a user process to the kernel and then back to the same user process many times. So each time we do any kind of I/O, at least if it's not DMA, it works like this. So we go to the kernel, we go back. And if every time we would switch the page table base register and we would traverse the page tables, this would take about 200 nanoseconds just for this kind of switching and traversing. And we want syscalls that are much faster. So syscalls now I think can be down to 100 nanoseconds only. So the idea is we can use our cool virtual memory for that. So we have a 64-bit address space. We never use all of that anyway. So why don't we just say, okay, the top part of the address space we use for the kernel, and the bottom we use for the process. And then we map this kernel address space into every single process we create. And when we switch to the kernel, we don't actually switch the page table. We just use a bit in the pages to say, hey, this is a page that belongs to the kernel. So we are not even forcing this kind of layout that the kernel has to be in the top. The kernel could be anywhere, right? But it's just that canonically people have done it this way. And now we can switch very cheaply. We can switch without changing the page tables by just looking for each access that we translate. We just look at this single bit. Furthermore, what the kernel usually does in all operating systems, no, there is a difference here. What the kernel usually needs to do is he also needs to map the physical memory, because the kernel needs to be able to do things like, okay, I have a DMA device and this DMA device wants to write into physical memory. Or there are other reasons why the kernel usually maps the entire physical memory in one consecutive part of its own address space. So it looks like this, right? We have this user address space part on the bottom here. We have our kernel address space part on the top here, and this is obviously not drawn to scale, otherwise it wouldn't work. We have our entire physical memory, which is a part of the kernel address space also. So that means if we are in the kernel, or if we can read the kernel address space, we can read anything that's in physical memory. That's pretty cool. And the mapping is contiguous. That will be important later too. In Windows, it's a bit different. Windows has 3 different pools for memory, like a page pool, a non-page pool, and some system cache. But let's focus on the Linux stuff here. So let's go back to this timing side channels. We talked a bit about this before. It should be pretty clear how this works now. So what we can do if we know that a cache line is, for example, 256 bytes in size. No, sorry, now I was confused. So what we can do is we know, okay, the cache is caches our stuff. So we can allocate an array of a certain size. At least it has to be the size of what fits in the cache, like one cache block, times 256. And we can make sure no part of A is cached. There are special instructions, for example, to say, please, if this address is cached, remove it. This is the CL flush instruction. But even if we don't have this instruction, we can get by just reading other data and making sure, okay, now this other data is in the cache, but not anymore this array A. And then we access this array A at address X times some stride. Here the stride is 4 kilobyte, because 4 kilobyte is one page. So even if like a page would be in the cache, each X would lead to a different cache item being loaded. And X is unknown, but we know X is 1 byte in size. So it's between 0 and 256. And now we read basically this I times the same stride for each value of I. And we know for each time we read, we will have a complete cache miss. This will not be in the cache, except for this one time where we actually loaded this by our previous read. And we can compare the timings for this, and we will see that there is like a factor of 100 at least difference between a cache hit and a cache miss. So this is this kind of side channel, right? So this is how we can communicate 1 byte. And this channel is actually pretty fast. So this is, we can, if we see this as a communication channel, we can use this in the order of 100 kilobytes per second. So for a side channel, that is quite good. And the interesting thing now, the big discovery that underpins both Meltdown and Spectre is that this also works if this access of AX times something doesn't happen because this needs to be happen in the code, but happens due to out of order execution. So even if this access, for example, would be completely illegal and there would have been a bounce check that says, no, don't execute this code. If it's executed out of order or speculatively, this timing stuff still happens. So this is the problem with this rollback. When people design this kind of Tomasulo scheme and this rollback, they only care about what is written in registers, but not what kind of timing side effects actually happen due to things being loaded into the cache. Okay, so now let's go on to the real Meltdown. So this is the code from the actual paper. So what happens here, we have the CX register, which contains some kernel address. This is an address which contains a really cool secret. For example, I don't know, some password from or SSH key or something like this that is in physical memory. And we have this a probe array, right? So this probe array was always the A array in the previous slides. And the address of this is in BX. And now we can have a code that tries to move 1 byte of at a location stored in RCX into, let's say, A, the A register. And obviously, we are not allowed to do this. So when we only execute this instruction, this will segfault. The thing is, this permission check is quite costly. So this permission check is not done in order, but basically the CPU says, oh yeah, okay, I need to access this stuff and also I need to do this permission check. But while I wait for this stupid permission bit to come to me and to check this, I can execute the next instruction speculatively. So what it does, it multiplies this value that is now in the A register by 12. So multiplying by 12 is like shifting, shifting by 12, it's shifting here, not multiplying. Shifting by 12 is like multiplying with 4k, right, what we did in the previous code. And then we just access our probe array at the proper offset. So this is basically just assembly for the C code that we've seen before. And in another code, in another part of the program that we control, we can actually do this kind of reading of the probe array and see what was the byte that we read from this address RCX. And we can do this at a speed of 10K per second. So this is how you can read any physical memory at quite a high speed. The only problem is, oops, well, I said all of this. The only problem is, how do we deal with this seg fault? I mean, this seg fault is still gonna happen, right? So this is basically a race condition. Will this out of order execution be fast enough to complete everything before this seg fault happens? And then this seg fault eventually happens, and yeah, maybe we have 1 byte, but not more. But what can we do? Well, there are 2 ways to fix this. We can fork this program before we execute this code, and in the child install a signal handler for this segmentation violation problem, and say, oh yeah, okay, this child needs to die because it had a seg fault. So kill the child, make another child, get the next byte. Another even cooler thing, so you can make this even faster with newest Intel technology, or actually I think AMD has something similar now, is transactional memory. So what transactional memory allows you is to say, execute all of this code in one block like it would be one atomic operation, and if anything fails within that block, act like this never happened, this entire block never happened. And this is normally used for kind of accessing a resource with 2 different things, like to replace, for example, codes with logs. But here this has an interesting kind of feature that if a segmentation violation happens within that block, it's just that this entire block doesn't get committed, but you don't get an actual seg fault. So this is a quite cool feature that lets you avoid this expensive fork and makes this even faster. This was obviously not intended, right? But it's a cool option if you are on. I think Haswell is the first CPU that supports this. You can use that. But also works pre-Haswell. So pre-Haswell, you can use the fork approach. Okay, so obviously we don't want to exploit stuff only. We want to mitigate this. So how do we mitigate this? Well, the first approach that is already deployed everywhere is kernel address space layout randomization. So instead of saying, well, we have the kernel in always the same virtual address, so that we can basically pre-compute, okay, at which address is then the physical memory mapped to, we can randomize this a bit. So this KASLR patch for Linux has, I think, 40 bits of entropy for the kernel layout. The problem is that this physical memory is still contiguous. So if we have some known values in the physical memory, which definitely we have because we are a fucking process, we can just write some canaries and we can search for them. And 40 bits is not that much. If you have, let's say, 8 gigabytes of physical memory, then 8 gigabytes is 31 bit, right? No, 33 or 44. Anyway, I calculated this at some point, and it's basically 128 tries, right? So you need to check 128 times with that thing for your canary value, and afterwards you know where is the physical memory mapped. And this channel is quite fast, so basically this is useless. This is useless because we map the entire physical memory in one contiguous space. So you might ask, okay, I get the idea why we need to map some physical memory, but why do we need to map all of them? And this is exactly what some people at TU Graz did. They developed this Kaiser patch. So they said, well, even I think they developed this before they knew about this Meltdown attack. So basically, they developed this patch because they said, well, this kernel address space layout randomization will fall if there is any bug which allows something like this. And then nobody took them seriously. And I think that motivated them also to look more into this topic. Because everybody was like, yeah, this is not really a problem. Paging works wonderfully. We don't need your patch. And now it's very important because now this is basically what prevents Meltdown. This Kaiser patch. Obviously, since Meltdown, it has been improved a bit. It's a good idea, but the problem is obviously now it costs more to do a syscall, right? Because now we don't have this cool thing that the kernel is mapped into every process address space, and some kernel memory still needs to be mapped due to how x86 is defined. So basically, there might still be some problems. The people who developed this patch are the same people that reported on this Meltdown stuff, so obviously they won't say, it doesn't work. Yeah, but it's interesting what will happen there in the future. But currently, so basically this is what everybody is installing now, right? So for Linux, this is called the Kaiser patch, and I think now post-Meltdown, it's called the KPTI patch set. And this is the same on Windows, this is the same on macOS, they are all using this mitigation technique. How could Intel fix this?
Can I ask a question?
Sure.
So at a 2 to 3x performance on syscalls, do you count it with things like PCIe? So I think there were some optimizations to use PCIe to kind of bring down, basically make it possible not to flush TLD caches and therefore still decrease the cost of syscalls.
Okay, that might be. So, what the fuck? I have some kind of warning that I should restart now. Okay, I will remind you tomorrow, Tobias, to restart this laptop. Maybe you didn't install the KPTI patch yet.
Actually not, yeah.
Nice. Okay, I didn't hear about that actually. So the only thing I heard was a lot of cloud vendors suddenly crying because obviously if you do any kind of virtualization solution, you are doing a lot of this jumping between user process and kernel process. And if suddenly your VM stuff is 3 times as expensive, but your pricing is already kind of factoring in that there is Amazon and there is Azure and there is I don't know how many other cloud providers, then you have a problem if you suddenly have to tell your customers, well, okay, I protected you from this meltdown, but suddenly you need to buy 3 times as much cloud servers and hope that your applications actually scales. Is not nice for them. So I think a lot of people are investing quite a lot of smartness into, okay, how can we mitigate this?
I think some of the VMs or some of the VMs just don't expose PCIe to the kernel, to the guest kernels, and that's potentially one of the reasons.
Nice. Okay, that is a nice idea. Okay, but basically, how could this be fixed in hardware? Well, the CPU needs to do this permission check before continuing speculative execution, right? This is a large performance penalty, obviously, for the CPU, because basically this needs to happen on every memory access now. So this serializes a lot of stuff that was out of order executed before. There are some ideas for making this check cheaper. So how about we don't use this bit in the page table that could be anywhere, but how about we actually tell the CPU, okay, if the address is in this kind of upper half, then it's always kernel memory and you are never allowed to use it. So we don't have to look at this page table stuff, but we just look at a few bits of the address. This would be much cheaper. The problem is this is not how x86 is defined, so this would be quite a big change. But probably nobody would be hurt by it because actually all kernels work like this already now. So this might be an interesting option. Also, what is interesting is the full meltdown attack, even though some proof of concept stuff works, has not been demonstrated for AMD and ARM, but for unknown reasons, right? It could just be that their out of order execution pipeline is not deep enough or something like this. We don't know. So with a different code, it might still work. So there is nobody from AMD or ARM that stood up and said, yeah, we always do this permission check. That's why we are slower than Intel, but we are more secure. So not like this.
Developers actually committed to exclude AMD processors from the, to exclude this workaround for AMD processors. Yeah. So there's a statement, I think, and there's a commit in the Linux kernel that actually says AMD is not vulnerable by one of the official AMD guys.
But we still don't know.
Yeah, but we still don't know why.
We still don't know why. AMD probably knows why, but
We don't.
we don't. Yes.
Yeah.
But there has been like investigation, and if you are from the correct group of people, you could know.
Okay, I'm not. So I was interning at Intel for some time, but not at AMD. So. Okay, so the other interesting thing, so this was all Meltdown, right? So, but this Spectre thing is actually very similar in the techniques it exploits. So Meltdown exploits the fact that out-of-order execution and this permission checking are not serialized. But what about normal branches? Can we do something there? So the main problem was this out-of-order execution, right? And this doesn't only happen with this permission check if it's kernel memory or not. This out-of-order execution also happens in any if you write. And yeah, we can, and this is Spectre. So Spectre doesn't rely on this address mapping of the kernel address space, but it basically says, okay, if you have any kind of user code and you have some secret stored in this user code and your user code is written correctly so that this secret could never kind of leak to the attacker that is just using this program, Spectre is saying, oh, well, you don't fully understand your CPU and everything can leak now. How we do this, we want to read a secret by k stored at address of k. X is an attacker-controlled integer value signed, and what we want is that some address of array 1 plus x equals address of k, because we found some code like this in the code. This is actually interesting. In the original paper they say that codes like this are common, but they don't actually demonstrate this. So I think this shows how quickly the paper needed to be written, because there were several teams working on the same stuff. So it's basically better to publish first with incomplete data. But let's assume that this code is very common, and we have this code in our application. And if we have this, then what the attacker can do, the attacker can do some training. So the attacker can make sure that array 1 size and array 2 are not cached, but k is cached. How can we cache k? Well, let's assume this secret is like a SSH key or something like this, and we can just force the web server to access this key, but in a valid fashion, right? Just to check something, and then it's cached, and we need to make sure this array size and array 2 are not cached. Let's assume we can do that. And we need to make sure that this branch predictor that makes this educated guess, if you remember, predicts that this condition will be true. This is quite easy, right? We can, for example, just run this code with a normal, non-malicious input a few times, and then this branch predictor thinks, yeah, x was always within bounds, so it's fine. So now what happens is that we pull line k into the cache, and we retrieve k again by measuring the access to array 2. So let's assume we have that code in the application. How can we do this? Well, one interesting application would be if we can do this, let's say we can write such code in JavaScript, and we can make a browser execute this JavaScript with that code inside. Then we can read any value that is within the process that executes JavaScript. So if the process is a web browser and this JavaScript is just on our website that we serve to the user, then we can, for example, check maybe the user needs help with his online banking. He always loses this password. Let's store it for him securely. So this has been demonstrated with JavaScript and V8 in Chrome. But this Spectre actually has one other kind of so this was what they demonstrated with this code that I showed before, and they did it once in C and once in JavaScript. Both worked. Obviously, the JavaScript gets just-in-time compiled, right? So basically, at the end, both is some assembly. Yeah. So the interesting thing about Spectre is also this branch predictor training. So what they found was to train this branch predictor is actually quite easy, because how this branch predictor works, it takes the address of the actual branch instruction, like of the jump or the read instruction. So you see some of these indirect branches here, right? And it takes the address, and it doesn't take the full address apparently. So some other group before reported that it takes the 30 last bits of the address. What they reported in the paper, where we checked on Haswell, and it was only 20 bits. Then this branch predictor also saves some stats, like did I take the branch or did I not take the branch, or how often did I take the branch, and of course the target address. So it says, okay, this jump that depends on the value of EAX 100 times was always landing at this address. So probably I can continue execution speculatively at this address, and hopefully I'm right. Obviously, I don't need to be, but I should be. So now if we use this, the fact that this branch predictor is actually not flushed if we change processes, we can just have one process that knows about the address in the other process and trains this branch predictor in the right way, and we can basically force speculative execution to go anywhere. If we have this kind of instructions in a known place, we can just say, okay, it's not like return-oriented programming, right? So we are not really diverging control flow, but we are diverging the speculative control flow, kind of. So this is the cool thing about this Spectre, that it's kind of part of the attack, but it's more than what they documented is this kind of feature that you can redirect this control flow, but only for a few instructions, but actually quite a few. So they showed that up to 120 instructions are executed out of order. So that is scary. How do we mitigate that? So Spectre actually doesn't work only on Intel, but it works on Intel, on AMD, and on ARM. So there everybody is kind of vulnerable, because it's much harder to mitigate, right? Because suddenly you need to look at every jump. It's not only the loads of some address, and you can just check if it's kernel memory by looking at the address. It's harder. So what compilers can do, like LLVM or GCC, is to find critical branches and block speculative execution. So you can basically say, okay, this branch looks critical. I don't want to, if I take this branch, I don't want to, or not take this branch, doesn't matter. I don't want to continue with speculative execution. You can put, for example, the CPU ID instruction there, or the mfence or lfence instruction. The problem is that these instructions are not really specified to block this speculative execution. This happens to work, but it's not documented that it always will. The nice thing is that apparently Intel at least said, okay, we acknowledge that this is really how they work, and we will add a sentence in the documentation or in the specification that says, yeah, they block speculative execution. So they are costly, and compilers can also try not to emit usable indirect branches. That is very difficult to do. Basically, you need to create from such an instruction that we saw before, like a jump depending on EAX, you only create a jump that jumps first by a fixed value, and then you have the indirect jump somewhere later. So this shouldn't be part of the talk. If you want to know more about this, the keyword to search for is red poline, so like trampoline, but for return instructions. So you don't return directly, but you have like one level of indirection. And both LLVM and GCC have this feature. Is this a good mitigation? Yeah, well, we need to recompile all the code with that patch that makes everything a bit slower. Would be preferred.
Is it confirmed that the red poline actually works on all the current architectures? I've heard some people questioning whether it works on Skylake.
Yeah, exactly. So it's not really sure if it works on everything. And the other thing is, Depends how long your out of order execution pipeline is, right? So basically you add some
essentially you probably, I think they're just trying to create some kind of speculated virus, right?
Yeah.
Right, but they capture the control flow in the loop. So that the speculative control flow is captured in the loop. It can't exit from that loop. So it might speculatively execute the loop all the time.
Mm-hmm.
But to my understanding, all this depends on the fact that they try to hint the processor in speculating in a certain direction.
Yeah, exactly.
This is not a documented architecture feature.
Exactly.
So the very basic idea is your returns are very, very common, so they're a very typical pattern. And so if you make sure your jump uses this typical pattern, then the CPU will not speculate in any other way, just because it believes this pattern is the most likely one.
Exactly, but it's
not documented. I mean,
exactly.
maybe it speculates in some situation, it thinks something else.
Like your branch predictor could just work differently, right? Instead of consulting this branch predictor and saying, okay, if you say this is likely, I will speculatively execute only in the likely direction, I could build a CPU that adheres to the x86 spec that basically just speculates in both directions for indirect jumps, or in multiple directions. I could just ask my branch predictor, okay, don't give me the most likely one, give me the 5 most likely ones and speculate on all of them. And then this capturing in a loop wouldn't work anymore. Yeah?
Wouldn't speculating on both jump be the best solution? Because you couldn't really.
No, because this is why people invented this branch predictor, right? Because this speculative execution is basically like opening another thread. So you are doubling your resource needs. And if you are doubling your resource needs every instructions, then you can't speculate very far. So this is why we have this branch predictor, and we are hoping that the branches are all predicted correctly.
It's also to not burn power, right? So you
exactly.
That this will happen very likely, and that also saves you from paying for the power.
Exactly. It's not only time, right? If you want to have a CPU that is as fast as possible and you have a lot of power, this would be a good direction to go in. But usually we need to care about both, because power is not only cost, power is also heat, and if you burn the CPU, it doesn't execute fast anymore too. Yeah?
So I'm not a computer scientist, so I hope the question doesn't sound very stupid, but what is the use of changing the compiler? If I am to write malicious code, I will use a compiler that doesn't have the fix, right?
No, but okay, so actually for this JavaScript kind of attack, you are right. There you could just handcraft this code. But the thing is that even for JavaScript, this is compiled at the client, right? So basically, if the client knows about this attack and doesn't compile the JavaScript code that you give in your browser in this vulnerable way, then this would also prevent the attack.
But with GCC, I use a GCC prefix,
Mm-hmm.
and then I combine malicious code with that, then I would circumvent it.
Yes, of course, this would circumvent it, but then you need to get your malicious code still to the client and execute it there somehow. I mean, otherwise, of course, you can exploit your own machine, but that is kind of boring, right? So if you can trick your target into executing this code that is compiled with an old compiler, then yeah, this is very nice.
And what about the antivirus technology? Can it try to catch this? Or
Maybe we should discuss this over beer, because this would be a longer discussion. But yes, so antiviral technology never works. It just increases your attack surface, basically. It's just like, okay, now you have this cool thing that needs to parse a lot of stuff. Most of the traditional bugs actually happen during parsing. And it needs to be updated constantly, so it needs this channel of, okay, I download code from the internet and then I execute it with root privileges. This and parsing are both great ideas. But from the attacker's point of view, not from the defense point of view.
So our KPI patch is actually for Windows disabled if you have an antivirus.
Sorry, I didn't get the question.
So I thought Microsoft actually does not enable KPI changes if you have a third-party antivirus installed.
Yes, I heard this as well.
Because it causes some issues. And the antivirus usually runs with all the privileges, so you actually can't crash our system. So it actually makes you less secure right now.
Maybe, do you want to close? Maybe we can move this to pizza and beer, and I will still be around for like an hour.
He was hungry, and maybe some of you as well. So, yeah, thanks again, Timo.